If we pick back up where we left off last time, so we introduced Chapter 4 in the Chamberlain-Bowles text, where we really focus on first law for closed stationary systems. That is, if it's a closed system, I'm only going to have heat and work crossing the boundary, so add the ends, that's heat in plus work in. Subtract the outs, that's work out minus heat out. And if it's stationary, the only type of energy that will change for my system is going to be the internal energy. So that's just going to be M delta U. And we said a lot of people will simply call it, they'll say Q minus W is equal to delta U, and that's fine as long as you understand if we do that, we're saying Q net in, right? So Q net in being the difference between heat in and heat out, minus the W net out, the difference between work out and work in, that equals M delta U. And that's okay. You'll see that in a lot of thermotechs. There's nothing wrong with that. That's just preserving what we call a traditional sign convention, where heat in is positive and work out is negative, but you have to keep that negative sign in front of the W to do that. Our text just says, you know what, just add the ends, subtract the outs, that equals the change. And I've grown to prefer that, honestly, but either way works just fine, as long as you can keep your sign straight. Now, what I wanted to do is let's continue on. Let's look at another example problem, make sure, okay, I don't have a glare on that. I've got a polytropic example here. This is probably not realistic. This is probably not something we would encounter. Polytropic is something you could encounter, but this particular example may not be something we would encounter. But that doesn't mean we can't work through it and see how the process works. This is more difficult than something I would put on an exam. With that said, I have and will put a polytropic on the exam. That's not what makes this one difficult. So let's just dive into this one. We'll see what the challenges are with this one. So just like any other problem that we're trying to solve, we've got to know what are we looking for. And this is a piston contains 0.3 kilograms of steam, given pressure and temperature. Cylinders compressed via polytropic process. Determine the boundary work if the final state is, and they give the final state, pressure and temperature. So all of that says we are trying to find the boundary work. And we talked about boundary work last time. We said let's just compute that in the out direction. Okay? If the system is expanding, it's doing work out. If the system expands, that means it's talked about that last time, right? We said if a system expands, then that boundary work out is going to be a positive quantity. And we said expansion, when it's going to a larger volume, you're going to get a positive quantity. That's because if that system's expanding, it's pushing into the surroundings. It's pushing the surroundings out of its way. The system is doing work to the surroundings, so that is work out. If the system's being compressed, so it's going to from a larger volume to a smaller volume, the system's not going to do that spontaneously. The system, the surroundings, something outside of the system has to push that system into a smaller volume. It has to compress it, meaning work has to go into the system, or the opposite of work out. So the sign here on the boundary work integral is going to determine or tell us the direction that work is actually going, the direction at which energy is actually being added to or removed from the system. So we'll talk a little more about that as we move along. So general problem solving says, what are you looking for, what do you know, and what are the tools you're going to use to get to a solution. So we're looking for the boundary work. We need to know, what do we know? Well, it's water. Again, this one says steam. Anytime it says steam, am I still on the screen? Yeah, just barely. So anytime it says steam, that we're referring to water, most likely in the vapor phase, but we've got a pressure and temperature there, so we can verify that. They've given me a mass, 0.3 kilograms. They've given me a pressure, an initial pressure of 2 megapascals, and they've given me an initial temperature there of 800 degrees C. The cylinder is compressed via a polytropic process. So they've given to me that it's polytropic. Polytropic, if you like. I say polytropic. Polytropic's fine. Determine the boundary work if the final state is, and they've given me a pressure and temperature there. So P2 is 1.6 megapascals, and T2 is 500 degrees C. Okay. Again, general problem solving says, what are you looking for? What do you know? What are some good tools to get you to a solution? Well, what are some good tools we would have to find the boundary work? The best tool we'd have to find boundary work, of course, well, there's two that come to mind. One would be the first law, but the problem with the first law, we could write the first law. That's a good exercise. If we look at what's crossing the boundary, we know we've got boundary work because it's a piston, right? So we know there's going to be boundary work. I'm betting this thing is losing heat, right? Because they've not said it's adiabatic. They've not said it's well insulated. It's not like Chapter 2 where you could say, oh, well, they didn't say anything about the heat. Let's just assume it's negligible. No, we could use the first law to find the heat. So the first law is going to have an unknown heat and this unknown boundary work. So it's going to have two unknowns in the first law. So again, what are some good tools to find boundary work? The first law is not a bad tool, especially if I know it's an adiabatic system, and it's probably the only unknown in the first law, or if I know the heat. But another thing you might do anytime you got a boundary work problem is just write out the boundary work expression just to see if you can quantify it or get enough information to try to get to a solution. Right? We talked last time, we said if the mass is constant, you can pull that out of the integral. Right? So again, boundary work is always going to be the integral of pressure as it changes as a function of volume. From the initial volume to the final volume will give you the work out. If the mass is constant, you can pull it out of this dV. Right? And now I'm integrating with respect to little v. So pressure times, integrate pressure with respect to little v from the initial to the final volume. Either of those are just fine, and we can move along from there. Okay, so we know the mass, right? We know to use the boundary work expression, I need to know how does pressure vary as a function of volume. Well, I do. I know because it's polytropic, I also know that PV to some power n, constant value n, is equal to another constant c. This is polytropic. This is what that word means. It tells you, when you see that word polytropic, it tells you, you know pressure is a function of volume. Or maybe the problem statement has said, if the problem statement gives you pressure is a function of volume. That's normally a dead giveaway that we can just use this expression to find the boundary work. Okay? Because again, to do this integral, I need to know how pressure is a function of volume. Well, here I do. I know pressure is equal to, you can see C over V to the power n, or if you like, my preference would probably be CV to the minus n. So I know how pressure is a function of volume. I just don't know these constants. I need to know these constants here, C and n. Okay. So if I could find C and n, there's two unknowns there. Now let's look at this expression and say, okay, well, this needs to be my only unknown. What else can I find? Which, by the way, this is the standard procedure you'd go through to try to solve a problem. Is I've got this expression. All right, which of these are unknown? Well, I know pressure as a function of volume. I do need to know C and n. So it doesn't look like it's helped me, but it does. I don't know these volumes. Those are also unknowns I got to account for. Okay. Well, do we have a way to find volumes? Yes. Look at your substance. What is your substance? We know it's water. I have property tables for water, and given two properties at a state, there's a good chance I can find all the other properties. So given pressure and temperature, I should be able to find the specific volume, right? Knowing that total volume is equal to mass times specific volume, I should be able to find specific volumes at state 1 and state 2. So I should be able to find the volumes or these specific volumes in either case. So I'm down to trying to find C and N. Those are my unknowns. I've got a lot of equations, and yes, I'm going to have a lot of unknowns. Well, welcome to engineering. There's not another way to put that there. That's just kind of what we do. We try to solve problems that look impossible on their face. Yeah, that's kind of what we do. So yeah, a lot of equations, a lot of unknowns. Let's talk about how do we find C and N. So normally C and N would be given to you in the problem statement unless it's kind of more of a realistic scenario where we don't know C and N, we're going to have to measure them. This is more of a realistic scenario. We don't know C and N, we're going to have to somehow measure them or approximate them using data that's given. So here's how we would go about that. P1 V1 to the power N is equal to a constant. So we know pressure at state 1 times volume at state 1 to this unknown power N is equal to a constant. And that constant also is true at all other states. So if you look at this, I've now got, assuming I can get the two volumes, which we've already agreed that I can, because I can get specific volumes at both states, we hope. So assuming the volumes are known quantities and we know the pressures, the only unknowns now are C and N. I've got two equations, see two equal signs, so two equations, two unknowns. Theoretically, that can be solved algebraically. I'm going to set this aside. It's not really helping me right now. So let's do some algebra, shall we? If we substitute around C, all right, so P1 V1 to the power N is equal to P2 V2 to the power of N. I'm going to do this kind of quickly here. This is not difficult algebra, but it may not be something you do on a regular basis, and that's okay. I'm going to say P1 over P2 is equal to V2 to the power N over V1 to the power N. Okay. Now notice, because they're both raised to the same exponent, I can, I guess, factor that out. I'm not a mathematician. I don't know if that's the right word. But they're both raised to that same exponent, so I can just raise that ratio to that exponent. Now remember this expression right here. We said mass times specific volume is equal to total volume. So I can say, well, you know what? Mass times specific volume at 2 divided by mass times specific volume at 1 is equal to N. Again, I'm not a mathematician, so I'm not afraid to use the word cancel out. So that mass cancels out. It's important to keep the mathematicians happy that we point out we know mass is non-zero. So since mass is non-zero, this mass can cancel out in layman's terms. And they don't like that word, but we don't mind it. That mass can cancel out. So if I can find specific volume at 2 and 1, which we've already said we should be able to, N becomes my only unknown. How do we find an unknown exponent? Somebody's mumbling under their breath, that evil devil spawn, the logarithm, right? The logarithm is how we find an unknown exponent. So here's where we're at. We got P1 over P2, known quantities, is equal to V2, the ratio of V2 over V1, little v2 over little v1 to the power N. And what you can do is you can take any log, I'm just going to use natural log, but the log of any base, natural log base e is just fine, of P1 over P2. And so I'm going to take the natural log of both sides of this expression, is equal to the natural log of V2 over V1, and it's the natural log of this to the power of N, which, if you remember some logarithmic algebra, and most of us don't unless you use it on a regular basis, this N can factor out. Right? So this becomes N natural log V2 over V1. And I got to stop there. So next thing.